Claudius Ptolemy's Astrological Travel Guide, Ultima Thule 79. Watching from across the Bay of Naples, the Roman writer Pliny the Younger, our only eyewitness source for the events of that day, described the strange cloud rising up from one of the distant mountains as resembling a pine tree lifted up high on an extremely tall trunk and spreading out into several branches. By Pliny recording, it was about the 7th hour of the day, or roughly 1 p.m. The date was August 24 in the year 79. The mountain, as Pliny would soon later, was Vesuvius, a long-dormant volcano just then waking up from its slumber. As Pliny goes on to narrate, it wasn't until the following morning, August 25, that an unstoppable wave of ice and debris, today called a pyroclastic surge, rumbled over and through the nearby towns. Pompeii, most famously, and Herculaneum were wholly entombed, reduced to a haunting exhibit of ancient Roman life, complete with buildings, paintings, and even of contours of men, women, children, and pets, exquisitely preserved at the instant of their deaths. Pompeii and Herculaneum received the brunt of Vesuvius' violence, but fainter ripples would have been felt much further afield, as with recent volcanic eruptions, sulfuric acid and other aerosols from Vesuvius likely with the stratosphere, contained the stratosphere from both reducing the amount of sunlight reaching the Earth and causing a modest cooling of temperatures across the globe. Chemical traces of the Vesuvius eruption of 79 have even been detected in ice cores from as far off as Greenland. It's probable then that in distant lands that had never heard of Rome, let alone Vesuvius, warming, trade, and the thousand facets of daily life that depend upon these activities were impended in subtle, perhaps not so subtle ways. The strewing of Vesuvius as over an apt geological analog for Rome's increasingly global research, even as the empire's political boundaries approached their maximum limits. Rome's role as a nexus within, as representing the interconnected international order, continued to grow. The Roman and Han Chinese empires, for instance, were certainly aware of each other, and the silk that came to symbolize Roman luxury ultimately originated in Chinese workshops, even if its export passed first through many middlemen. And in the reign of Pompey itself, an extraordinary ivory statuette of the Hindu goddess Lakshmi was found, evidence that the traveling ships of the ancient world carried not just commercial but cultural and spiritual cargo as well. Bounded amid such way, astrology too was doubtless transported to the far corners of the world and back many times over. Did Roman knowledge rival Vesuvius in reaching as far as Greenland? This seems unlikely, for the Greco-Roman writers of antiquity, the northernmost spot of the known world was a place called Thule, or as Virgil put it more melodiously, Ultima Thule, Virtus Thule. There's a tradition associating Thule with Greenland. The United States even maintains a military installation there called Thule Air Base, but whose actual location has long been a mystery. The ancient geographers were extremely fudged about Thule, not only with regard to its location, but even as to whether it was an island or a continent. Much like Plato's Atlantis, Thule has come to signify a lost world situated just beyond the borders of our knowledge. But though Thule lacks precise coordinates, the heavens as seen from its high northern latitude can still be reconstructed at the moment of Vesuvius' eruption. Thule's sky would have been configured very much like Figure 5.1. while the facts surrounding the tool's location is an extreme case. Uncertainty about the basic contours of the globe was simply a fact of life for ancient map makers. These cartographic limitations doubtless seem incongruous to an empire like Rome's, which had pretensions of being the epicenter of earthly power. But this wasn't an issue which Roman arms or Roman laws could subdue. The problem of mapping the world is fundamentally a problem of astronomy because the only way to know your position on the globe with certainty is to measure it with reference to rotating the sky. Yet the only way to have accurate measurements of the sky is to first be certain of where you are on the earth. This is a cosmographical pickle, if ever there was one. Who then, given the technological impediments of antiquity, could ever hope to find the Earth's proper place or elite their own within the disorienting vastness of the cosmos? The greatest. It has been said that the importance of a scientific work can be measured by the number of previous publications it renders superfluous to read. Otto Neugebauer, the historian of science, which is responsible for much of today's knowledge about ancient mathematical astronomy, cited the adage to explain what essentially nothing survives of Greek astronomy prior to the time of Claudius Ptolemy. Quite simply, Ptolemy's brilliance obliterated everything that came before. Concerning Ptolemy's life, there is not much to be said. It can be summarized that he was born around the turn of the second century, maybe a decade or two after Vesuvius, and that he lived, worked, and wrote in Alexandria, the capital of Roman Egypt. But with regard to his scientific writings, it is impossible to say too much. Ptolemy's most significant work, the Almagest, established a unified mathematical framework for computing the position of the sun, moon, stars, and planets at any time in the past, present, or future. So comprehensive and so compelling was the Earth-centered cosmos. It described that Almagest will remain the final word in astronomy for nearly 1,500 years, until it was finally superseded by the sun-centered system of Copernicus and Kepler. No scientific work, with the exception of Euclid's element of geometry, has never remained so authoritative for so long, and it seems safe to say that none that to say that none ever will again. The Almagest's original title was Mathematicis Syntaxis, or a mathematical treatise. But this nickname is it acquired over centuries of study. The Almagest is an affectionate testament to its place of honor in not one, not two, but four separate civilizations. First, there's the Des, Ils, Els, Dergs, and Les, with the various modern languages prefaced in medieval name. Almagistum, in turn, is a Latinization of the Arabic Al-Majisti, itself an abbreviation of the Greek Himegisti. In Greek, Himegisti means simply the greatest. The Almagest was the greatest of all the ancient treatises on astronomy, just as Ptolemy was the great of all the ancient astronomers. Somewhat less well known is that Ptolemy was also the ancient world's greatest geographer and its greatest, or at least most well respected, astrologer. As above, so below. It's a mind-boggling to consider that one individual could stand at the summit of so many different mountains of knowledge, and yet Ptolemy would have considered his astronomy, geography, and astrology as simply separate ascents to the same destination, an abstracted view of the cosmos in the fullness of its majesty. In this context, it becomes less surprising to learn that Ptolemy's Almagest, on which his fame chiefly lies, was the earliest of these major writings. But then again, neither his geography nor his astrology could have been written without it. Ptolemy was frustrated knowing that astronomical records from cities other than his own Alexandria were of no use to him or if their precise geographic relationship to Alexandria remained uncertain. Conversely, Ptolemy could then generate useful astronomical tables for other cities if their geographic coordinates were no better than rough approximations. Accordingly, once Ptolemy completed the Almagest, perhaps around the year 150 or so of the Common Era, he turned his attention to his next great project, geography. Ptolemy knew that the only way to really measure geographic distances was with astronomy. If two observers in two different cities record the time of the same celestial event, such as a lunar eclipse, then the difference in time can be converted to a distance on the globe. Fortunately, the only eclipse Ptolemy notes as even having been measured this way with the eclipse preceding Alexander the Great's victory at Gaugamela, for which Ptolemy had records from Arbela, now Erbil, Iraq, and Carthage, near modern-day Tunisia. The comprehensive solution to Ptolemy's cartographic conundrum would have been a global mapping survey, one that dispatched teams equipped with astronomical instruments to the far ends of the earth, much like the 18th century expeditions of Captain Cook on his ship Endeavour or Lapérouse on his ship Astrolabe. But an establishment on that scale was beyond the ambitions of even someone of as far-sighted as Ptolemy. Instead, he had to settle for organizing the scattered scraps of geographic knowledge handed down to him by his predecessors. Yet, it's these scraps, or at least Ptolemy's attempts to make sense of them, which gives us our best peek into the far-flung trading networks of the ancient world. They even record the names of Greek and Roman explorers who ventured as far south as sub-Saharan Africa and astonishingly as far east as Vietnam. Ptolemy's objective for the geography was to catalog, for the first time ever, the latitudes and longitudes of the major cities and landmarks of the inhabited world. This was the region known in Greek as the Ecumene, from which the modern word ecumenical derives. To this end, Ptolemy computed the coordinates for locations as far west as the Canary Islands or Islands of the Blessed, and as far as is the metropolis of Chinese, a city which may have been referred to Luoyang, the capital of the Eastern Han Dynasty. The northernmost extent of his geography was the latitude of Thule, a line he drew at 60 degrees north of the equator, skirting the sphere. Within the geography, Ptolemy managed to compile an impressive list of nearly 8,000 latitude and longitude peaks. But the purpose of the geography wasn't to make a list, it was to make maps. In this, Ptolemy, even more than the explorers he described, ventured into truly uncharted terrain. By being the first to address head-on the mathematical challenges of mapping the Earth's sphere onto a plane, Ptolemy is rightfully the first true cartographer, An issue is hard to comprehend in the mind's eye. The totality of the Earth's geography, both large and small, because even an accurate spherical globe shows only half the Earth in any one view. Meanwhile, on a more granular scale, it would be completely impractical to make a globe big enough to show details helpful to a traveler like city streets or river crossings. Flat maps in principle can solve both of these problems. Yet, as with most things, you can get something for nothing. It's simply not possible to transfer points from a sphere to a planet without losing important information in the process. The simplest flat map converts the Earth's latitude and longitude into evenly spaced lines on a rectangular grid. While this had the benefit of displaying the entire globe all at once, it doesn't do a good job showing what the continents really look like or the correct relationship to each other. The Mercator projection, Figure 5.2a, familiar from school classrooms the world over, partly solves this problem by ensuring that north-south distances are kept equal to east-west distances at every point. In particular, if if you wanted to sail from, say, the port of Shanghai to the Panama Canal, a Mercator map will tell you the right compass bearing to follow. This is a really nice property for a map to have, but the trade-off is that regions near the poles such as Greenland now appear enormous. To fix this problem, the Peters projection figure 5.2b shows the areas of the Earth's landmass in the correct proportions to one another. Since the Peters map diminishes the visual importance of the more northerly countries, it has become popular as a sort of anti-Mercator map. But the trade-off here is that it doesn't represent angles correctly at all. If you were to sail from Shanghai to Panama along the compass bearing taken from a Peters map, you'd end up making landfall near Lima, Peru, some 1,500 miles south of your intended destination. Unfortunately, it's not possible mathematically to make a flat map that simultaneously preserves angles like a Mercator projection in areas like Peters projection, although it's certainly possible to make a map that preserves neither. All flat maps have to make a compromise. Ptolemy, for his part, experimented with several mapping styles, each of which strikes a different balance of mathematical and visual characteristics. A few of these styles remain widely used even today. In the geography, for instance, he presents the first ever description of a conic projection, of which figure 5.6 is an example. Yet terrestrial charts like these of coastlines and capitals were to Ptolemy merely a warm-up. There was another sphere beyond the earth whose contours he still wished to trace, an image of the world in a separate substratus called the planisphere, of which only an Arabic translation survives. Ptolemy gives a mathematical description of an elegant and versatile mapping technique called stereographic projection. This technique remains even today hugely important in disciplines ranging from mathematics and astronomy to optics, crystallography, and electrical engineering. Stereographic projection is also the basis of the astrolabe, an ancient and beautiful astronomical instrument, and the graphical inspiration for all the themes of Heaven's book. For a basic idea of stereographic projection, imagine looking down on a globe from above its north pole and then scratching it onto its projector into its equator. The visual effects the visual effect ends up looking like a scoop of ice cream that's melted onto a warm plate from the bottom out, because there is no limit to how far outward these maps spread. It's customary to extend them only as far south as the Tropic of Capricorn. The nomenclature projection stereographic projection belongs to the family of maps that preserve angles, but the special magic of a stereographic projection is that it takes any cycle you can draw on the spherical globe, no matter the cycle's size or location, and converts it into a corresponding cycle on a flat map. In other words, stereographic projection keeps cycles, it doesn't transform them into more complicated curves, since the various geocentric coordinate systems of astronomy consist entirely of cycles drawn on the celestial sphere. A stereographic map provides an elegant way of displaying all of this together at the same time. Ascensions and declinations, ecliptic longitudes and ecliptic latitudes, azimuths and elevations, even the hours of 7 on the stereographic map, they are all drawn as simple circular arcs. Figure 5.3 shows stereographic projections of both the celestial sphere and the more familiar sphere on the Earth. To make a stereographic mapping of an entire Ptolemaic cosmos, all you would need to do is place the star map directly on top of the Earth map. The revolution of the heavens can then be simulated by keeping the Earth map stationary while the star map rotates clockwise once per day. Construction of two stacked stereographic maps provides the basic blueprint of an astrolabe. On an astrolabe, however, the terrestrial map is only implicit. What's shown instead is the horizontal coordinate grid, that is, the azimuth and the elevation lines for the spot where you happen to be. No matter where you are on Earth, you have a view of exactly one half of the celestial sphere. The plane of your horizon divides the celestial sphere into two equal hemispheres, and you can see the hemisphere up above your head. What this hemisphere looks like when plotted on a stereographic map centered around the North Pole can be a little tricky to visualize. Figure 5.4 shows horizontal grids and seated for observers at 4 different latitudes. The appearance of the grid at 90° north is probably easiest one to intuit. The orders can then be understood by comparison. In practice, astrolabes would come with several of these plates, which could be swapped in or out depending on where you were placed. For latitudes south of the equator could be constructed in a similar way, where the tropic of Center and Capricorn would need to be switched. Now, if on top these terrestrial plates we keep just the ecliptic cycle as an abstraction of the celestial map, we'll end up with an image of the cosmos that's starting to look a lot like scenes of heaven which appear in this book. The most conspicuous difference is that this image would look quite barren without the sun, moon, and planets. Unlike Archimedes' clockwork model of the universe, astrolabes as, astrolabes weren't designed to dissimulate the complicated orbits of these heavenly bodies. However, if you have a set of handy planetary tables like the ones of Almagest taught you how to make, you could look up each planet's ecliptic coordinates for a given day and mark them on the ecliptic cycle, just as we've done in our sims. Then, by rotating the celestial map clockwise to simulate the sky's daily rotation, the astrolabe will tell you at what time each heavenly objects will appear in different parts of the sky. In particular, the rising time of any star or planet can be determined by noting when, in its rotation, it crosses the horizontal line for your latitude. This remarkable capability is of supreme importance to astrology, and we'll have more to say about it in the next chapter. A means to an end. Without astronomy, there can be no astrology. That much is pretty clear. In order to assess the influence of the planets, you first need to have at least some capability of determining where those planets are, where and will be. The technological operations of astronomy are the building blocks that enable the abstract ideas of astrology to take shape. And just as musician understands a piece of music in certain ways, a pure listener does not. The ideas of astrology will be understood very fairly by someone who is familiar with the technological practices that give expression to those ideas. Insofar as Ptolemy's Almagest represents the most significant record of these practices, Otto Neugebauer, the historian of science we met earlier, draws a line in the sand. Any serious student of ancient or medieval astronomy must familiarize himself with these details, not only in order properly to appreciate one of the greatest masterpieces of scientific analysis ever written, but also to be able to understand what was common knowledge for every competent astronomer from the 2nd to the 17th century. Words to be sure. And yet the book look look like this is hardly the place to get into the intricacies of planetary orbit calculations, ancient or modern. For one thing, the astrology as a consumer, not a producer of astronomical data. In principle, the only astronomy as an ancient astrologer needed to know was how to look up a planet's coordinates in tables compiled by an ancient astronomer, even if in practice these were often the same person. Similarly, today we can take for granted that highly accurate astronomical data is never more than a mouse click away. Specifically, all of the planetary data that I used in this book comes from Horizon's online ephemeris system of NASA's Jet Propulsion Laboratory. The service provides public access to the same high-precision data used for interplanetary spacecraft navigation and for generating the astronomical almanacs published each year by the United States Naval Observatory and the United Kingdom Hydrographic Office. But what about the other side of this relationship? Will astronomy as we know it exist without astrology? The respectable applications of timekeeping, calendar regulation, and navigation have always been the chief motivations of observing the sun, moon, and stars. But the planets, historically, there was never a single application that required knowledge of the positions of the planets other than astrology. And it was the challenge of accurately predicting the orbits of the planets that ultimately gave rise to the scientific revolution and, from there, our modern technological world. Of course, it's possible that for centuries, astronomers were compelled to address the minor inconsistencies in the orbit calculations of, say, Mars for purely theoretical reasons. I wouldn't bet too much on it, though especially when so many of these same astronomers were so deeply committed to addressing the practical problems of astrology. In this, they were only following in the footsteps of the greatest of the predecessors, Ptolemy's astrology. The Ptolemy, the most famous scientist of the ancient world, also wrote a book on astrology in a seemingly minor detail that, upon reflection, probably single-handedly ensured astrology's revival. It's as if Einstein had followed up his theory of relativity with a book on the physics of crystal healing, which, to be clear, he most assuredly did not. A millennium and a half later, When Copernicus arrived at the University of Bologna, Ptolemy's astrology book, the Tetrabiblos, was still required reading in the astronomy curriculum, which in turn was mandatory for anyone pursuing a medical degree. This connection between astrology and medicine is one of long-standing importance. For many centuries, physicians were expected to make the diagnosis and time the prescriptions according to the planets. Like his geography, Ptolemy framed astrology as a natural extension of his astronomy. Or, as Ptolemy put it, his Tetrabiblos was about making predictions by meaning of astronomy, the astronomias. According to Ptolemy, these predictions came into varieties. The first, treated earlier in the Almagest, concerned the future positions of stars and planets. The second, the subject of Tetrabiblos, considered the effects of these heavenly bodies of their surroundings. Ptolemy's use of the word astronomy in the opening of Tetrabiblos is significant because it contributed to the thorough blurring of astronomy and astrology that persisted right through the end of the scientific revolution. Breaking the convention established by Aristotle, Ptolemy never makes use of the word astrologia. Even more surprising is that in the Almagest, the single most important astronomy book prior to Copernicus, Ptolemy never uses the word astronomia either. Instead, Ptolemy insisted that the Almagest was explicitly a work of mathematics, and he explicitly identifies his predecessors, including the great Hipparchus, as mathematicians. And let's not forget that for Ptolemy's original title for the Almagest was the Mathematica Syntaxis, voluntarily non-technical writings from the Roman Empire, such as Petronius Satricon, a mathematician, Mathematicus, was always and unambiguously as an astrologer. All of this is extremely confusing, but that is exactly the point. The modern distinction between astronomy and astrology is very difficult to project backward into the past. This isn't because the distinction wasn't acknowledged conceptually. It was, but more because there was rarely a distinction between an astronomer and an astrologer professionally. Indeed, Ptolemy himself was the model for this. For Ptolemy, the more meaningful distinction was within his second type of astronomical predictions, what we will call astrology, which he divided into subcategories: general predictions about the weather and environment and the destinies of cities and countries, and genealogical predictions from Greek for birthday about the destinies of individuals. This notion of two astrologies, or both astrologies, meaning general and individual, was revived during the Renaissance and referenced frequently by thinkers like Tycho Brahe and Johannes Kepler. In Greek, Tetrabiblos means the four books. This device only that the work was divided into four extended sections. The Tetrabiblos is extremely detailed and, on this account, extremely fascinating. But since Ptolemy insists on keeping the Tetrabiblos on a high philosophical plane, it's definitely not the book you would choose as a handy practical guide, given its a most complete lack of examples. Trying to learn about astrology from Tetrabiblos a bit is like trying to learn how to cook from a cookbook with no recipes. Instead, the Tetrabiblos seems to have functioned as a sort of astrological referee, providing an official opinion on topics that were otherwise subject to a range of conflicting interpretations. We've already seen, for example, how Ptolemy's adoption of the solar over the sidereal zodiac settled the question of what to do about the precision of equinoxes in chapter 8. We'll see that arguments over how to draw the house of heaven likewise hing on Ptolemy's instructions. Similarly, it's in his role as astrological beater that we too now run to Ptolemy. tables 5 and tables 5.1 and tables 5.2%. Ptolemy's definitive list of some of astrology's most basic groupings, the genders and influences of each planet, and the genders and planetary rules of each zodiac signs. Astrology. Early in this book, I suggested that all of the operations of astrology are nothing more than the assertion of linkage in time. The fact of introducing all these extra attributes is, in a sense, to open up new dimensions for expressing the ups and downs of these time-based relationships. The most important of these dimensions are those which to bring astrology a sense of space. The 12 zodiac signs are real true pieces arranged around the ecliptic cycle in a fixed sequence. Because of this, each sign and by extension any planet that happens to be wandering to it has a geometric relationship with every other. These relationships are called aspects, and traditionally five were recognized as being astrologically significant: conjunction, opposition, sextile, square, and trine. The power of the power of an aspect found expression in geometric shape it formed around the zodiac. For instance, all of the signs in sextile aspect which each other belong to one of two hexagons. The signs in square the sign in square aspect belong to one of three squares, and the signs in trine aspect belong to one of four equilateral triangles. These triangles, also called trigons and triplets, were in addition commonly associated with the four classical elements each earth a word and 5 figure 5.5 fittingly as our sim or heaven for this chapter shows. At the moment of Vesuvius eruption, the three corners of the very trigon were all occupied. The sun is Leo, the moon is the sun in Leo, the moon in Sagittarius, and Mars in Aries. Meanwhile, there is no shape you can make by condition every fifth sign, which is why this relationship was not recognized as a meaningful aspect. Furthermore, in what would seem to be an astrological pessimistic view of gender relations, aspects connecting signs to the same gender, conjunction, trine, and sextile, were considered harmonious, whereas aspects of mixed gender, opposition, and square were regarded as unharmonious. The belief that spatial relationships in the sky resonated in a correspondingly spatial way over the earth is one of the most ancient ideas in astrology. The Babylonians, for instance, held that the rival kingdoms to the north, south, east, and west of them were signified by the corresponding quadrants of the moon during a lunar eclipse. Similarly, Manelius alluded a handful of verses in the Astronomica to listing which zodiac signs ruled over which nations. But far and away, the most elaborate system of linking celestial and terrestrial real estate was the one described and very possibly invented by Ptolemy. Out of the four books of the Tetrabiblos, Ptolemy devotes nearly the entirety of the second, which is about general astrology, to his system of astrological geography. It's a remarkable section insofar as it's the only place in all of his writings where Ptolemy unites astronomy, astrology, and geography together. Ptolemy's basic idea is to assign each of the four quadrants of the inhabited world, that is the ecumen, to one of the four zodiac triplets. The ecumen, according to Ptolemy, could be curtained by the line of latitude passing through the pillars of Hercules and the Gulf of Issus, approximately 36 degrees north, and the line of the longitude passing through the Red Sea, the Black Sea, and the Sea of Azov, approximately 36 degrees is in modern terms. This placed the center of the document pretty much right on top of the ancient city of Antioch, the capital of Roman Syria, not far from modern-day Aleppo. Ptolemy referred to the resulting quadrants as Europe NW, Scythia NE, Southern Asia SE, and Libya SW. Additionally, each quadrant was subject to two of the four cardinal winds and two of the four beneficent and maleficent planets. I've mapped this system, along with a number of locations which play a role in our story, in Figure 5.6, using Ptolemy's very own conical map projection, the same one he introduced to the world in his geography. Ptolemy's astrology is without a doubt the most colorful part of the entire tetrabiblos. After outlining his basic quadrant scheme, Ptolemy races through a remarkable list of 73 different regions, asserting that the quirks and idiosyncrasies of each one's inhabitants are merely the natural product of where they reside on his astrological world map. It's a little bit like reading a glossy travel guide to ancient world, full of exotic descriptions of far off lands. Mostly too, it's like listening to a curmudgeonly old man spew a litany of ethnic stereotypes, except that in this case, most of the cities ceased to exist some 1500 years ago. Troglodytes, there are still superstitions given to religious ceremony and font of lamentation, pavilions, they are exceedingly depraved, several laboratories rascally are to be found in mercenary expeditions, looting and taking captives, enslaving their own peoples, and engaging into exclusive wars. One can only imagine what he had to say about these groups in private. Calvinistic though it surely was, Ptolemy's astrology was hardly a pointless digression. His purpose, like that of these eight sporandex, was to address one of the most persistent objections to astrology. How can astrology be valid if a civilized Alexandrian like Ptolemy could, in principle, be born under the exact same stars as a savage barbarian from Germany? Assigning different regions of the earth to different regions of the sky was a way of astrology to account for ethnic differences. Unfortunately, the inhabitants of the ancient world were hardly less fixated on race and ethnicity than, than are than are the modern descendants today, even if the tetrabiblos underscores how arbitrary these divisions could be according to Ptolemy. For instance, there were 7 distinct ethnic groups around the Aegean Sea alone, whereas Britain, France, and Spain were each regarded as completely homogeneous monoliths. Spirits Ptolemy's survey from the simple jingoism. However, his attempt to ascribe the ethnic differences he perceived to a set of rational principles. On this account, the tetrabiblos is one of the earliest examples of what's sometimes called anthropological ethnology, and unlike the blood-based racial theories which become especially pernicious in America and Europe, is the 19th and 20th centuries. Ptolemy's ethnology is entirely geographical. This makes the tetrabiblos rightfully the great-grandfather of what's surely the most famous modern work of geography anthropology, Jared Diamond's best-selling Guns, Germs, and Steel. But let's not be coy here. What really makes Ptolemy's whirlwind world tour so entertaining is all these sex, or rather how candidly Ptolemy discusses the sexual habits of the peoples how he describes, adding to the tetrabiblos long list of pioneering achievements. Therefore, we can also credit it with being one of the first to examine astrosexuality, which is the idea that your sexual predilections and romantic compatibilities are determined by your astrological makeup. Among the gossipy astrosexual tidbits in Theatetra Biblos, the one that comes closest to a general theory is the claim that attitudes toward homosexuality are distributed along a geographic gradient running northwest to southeast. The most tolerant views, according to Ptolemy, are to found the farther you venture into northwestern Europe in the regions ruled by the fiery triplicity, or as Ptolemy put it in the standard, rather polite translation. Because of the occasional aspect of Jupiter and Mars, they are without passion for women and look down upon the pleasures of love, but are better satisfied with and more desirous of association with men, and they do not regard the aspect as a disgrace to the paramour, nor indeed do they actually become effeminate and soft thereby, because their disposition is not perfected, but they retain in their souls manliness, helpfulness, good faith, love on kinsmen, and benevolence. Conversely, by the time you've reached the Middle Eastern countries of the ethnicity, attitudes have become downright hostile, to the point where they hold in the discussion such relations it melts in the eye of the beholder. Ptolemy's assertion that the sentence of homosexuality decreases along a line running from London to Yath agrees pretty well with what I imagine is the current conventional wisdom on the matter. Could he be onto something toward a quantitative veneer to this question? We can use that favorite tool of data analysis everywhere, a linear regression. Linear regression is one of several techniques used to gauge how strongly two lists of numbers are correlated. One of these lists, for instance, could be scores indicating how positively or negatively homosexuality is viewed in each country. As an especially detailed example, there's the Spartacus Gay Travel Index, published every year as a part of Spartacus International Guide. In the Spartacus Gay Travel Index 2017, each country is given points in 14 different categories ranging from the application of death penalty for homosexuality to the legal status of gay marriage. Adding these points together results in a more or less continuous score from +9 Sweden and the UK to -14 Somalia. The US, incidentally, only 8 cases out of 4. Of course, this list ultimately represents nothing more than the subjective assessment of the editors of the Spartacus International Gay Guide, but since their methodology is applied in a consistent way, using publicly available data, and most importantly, it includes every country, it gives us an excellent list to use. Besides, what data set could be more appropriate for a Roman term, while a Trojan themed regression, than one named after Spartacus, the leader of Rome's most fearsome snafu revelations, who made his encampment on Mount Vesuvius. As for the second list of numbers, this should indicate how far each country is situated in either the southwestern regions ruled by the very triplicity of southeastern regions ruled by the earthy triplicity. If all we needed was an east-west measure, things would be easy. Is that in that case we could just take the longitude of each country's capital city. Our situation is really no different. We can simply tilt the globe so that its near equator becomes the great cycle passing through the center of Ptolemy's astrological world map at a 45-degree angle. This is the dotted path down in figure 5.6. Then the longitudes computed with respect to this new equator will serve as a measure to the weariness or emptiness of any location. So are these two lists of numbers correlated. A linear regression figure 5.7 suggests that they are. Specifically, the regression's base fit line tells us that for 10 degrees of 5 Earth longitude we travel, we can expect that Spartacus Gay Travel Index score to drop by about 2.5 points. Regressions like this are a fixture of technical and scientific reports. But what do they really mean? In the previous chapter, we rejected several astrological claims when statistical tests showed that no correlation existed. So if we're being fair, shouldn't this analysis, which indicates that a correlation does exist, compel us to accept Ptolemy's astrosexual theory? Not so fast. As the saying goes, correlation does not equal causation. With enough data sets to choose from, it's not difficult to find two that are correlated, and it can become a bit of a sport to pick out the most absurd or humorous cases. For example, the correlation between the number of civil engineering doctorates awarded per year and mozzarella cheese consumption in the United States. But if so many correlations are spurious, then why bother reporting them at all? This is an important question, especially since misrepresenting correlations is undoubtedly the most common way people use statistics to deceive both themselves and those around them. Plate 6. One answer is that a strong correlation does indeed provide evidence in the support of theory, even if it must remain just one piece among many. How the pieces are to be weighted is ultimately a question of human judgment, one for which no single algorithm, test, or procedure will ever fully substitute. As a case in point, the data we plotted in figure 5.7 are hardly the only information we can bring to bear on the question of geographical attitudes toward homosexuality. It's no secret, for instance, that northwestern Europe historically, and even quite recently, was not especially welcoming toward homosexuals. Indeed, when the great Victorian explorer Richard Burton developed his own theory of geographical influence sexuality, the Middle East was explicitly included and England excluded from his map of what he termed the Zodiac zone, a region where homosexuality was supposedly natural, accepted, and common. Where figure 5.7 to be redrawn with the data from 550 years ago, with 150 years ago, therefore it is altogether likely that the best fit regression line will have entirely the opposite slope. Yet a correlation that shifts from one moment to the next undermines any argument that takes a fixed principle to work. Instead, perhaps the only constant uniting Ptolemy's and Burton's theories is that each imagined the sexual marks of faraway lands to be radically different from what he knew back home, and each projected his disgust or desire accordingly. That's hardly the story you would tell. However, if the only information you had was the cold and context-free data of figure 5.7, trying to figure out which story, if any, is hiding in your data is challenging, especially because there are usually multiple stories which can be crafted, and deciding which one to emphasize rarely has anything to do with the data itself. In the tetrabiblos, Ptolemy intimates an awareness of this problem when he pauses to reflect upon the sheer number of astrological possibilities. It is of course a hopeless and impossible task to mention the proper outcome of every combination and to enumerate absolutely all the aspects of whatever kind, since we can conceive of such a variety of them. Consequently, questions of this kind would reasonably be left to the enterprise and ingenuity of the mathematician. But what astrology teaches us, and what Ptolemy perhaps failed to appreciate, is that with enough data and with enough enterprise and ingenuity, the mathematician can generally make whatever connections he or she wants, and therein lies the danger, because as with exploring the world, so too with data, all too often you find only what you were looking for.